Hello friends, welcome to C Field Academy where we learn together from each other. So today's topic is data structures and we are going to discuss linked list as part of the data structures. So let's get started. So these are the items or the subtopics which we are going to cover as part of the linked list. So first we will start with an introduction to linked list, the definition and its applications and what it is composed of. Then we will jump on to see what are the different operations that are normally possible on a linked list. Then we will move on to its implementation, how a linked list is implemented in a language, the basic component, and how a list is actually created out of nodes. Then we will move on to each different operations of linked list and go into detail. We'll start with the insert operation and then see the pseudocode algorithm, and then with a detailed example. Similarly, we will then go through the remove operation, the search operation, and then the size operations. Then we will move on to see the complexity analysis for each of these operations. Finally, we will discuss different variants of linked lists that are used as part of computing environment or as part of computer science. And finally, we will end with a short exercise for you guys to try it out. So let's start with first what a linked list is. So linked list is a data structure which is a little complicated than the array. In array, if you remember, we had the elements that are present in contiguous locations, or in memory they are located one after the other, and then an element in an array can be easily accessed using an index. But linked list is different. It consists of a collection of nodes, not just which together represent a sequence, but they may not be stored at contiguous locations. So which means in every node there are two parts. One is the data, which is the actual data that is part of the linked list, and then there is a pointer, the next pointer, which tells us the memory location of the next node. So something like this, you can see a node is this, and we have a data part. In this case, A is the data, and then there is a next pointer that points to the next node. And in memory, these nodes may be located at different locations. They necessarily may not be contiguous, and every node has a link to the next node, and that's how it goes. And the last node in the linked list will point to null, which means it doesn't point to anything, indicates that the linked list is ending here. And then there is a special pointer, which is a head pointer, which points to the starting of the list. So the advantages of linked list as compared to the array is its efficient insertion and removal of elements. So you can very easily insert and remove an element from any position. There's no need to swap or move elements to make space as we need to do in case of an array. However, there are some issues as well, some disadvantages. Let's say we want to traverse to a node, we have to start from the starting. We cannot directly jump on to node C, let's say. So that's why accessing a node needs traversal from the first node. So we'll have to start from A, in fact from the head, then A, B and C, then only we will reach C, as compared to an array where you can directly go to the third index and then reach C. Not only that, there is also extra space that is needed, which means for every node we need at least two things. One is the data, which the size of which depends on its data type, and then a next pointer to point to the next node. But then there are various applications where linked lists actually finds itself very useful, and some of these are representation of graphs, sparse matrices, or representation of polynomials, which we do in maths, and then dynamic memory allocation. So which means we don't because the elements need not be stored in contiguous memory, so we can slowly allocate memory based on the need from any location wherever it's free, and then make our linked list by pointing each node to each other. That's why we see it in dynamic memory allocation. Alright, now let's go ahead and see the different operations that are present in a linked list. Basically there are 4 operations, in fact 3 main operations that are possible. The first is to insert, which means adding an element to a position in a linked list. So this involves adding a new element into an existing linked list. Sometimes it may be start, sometimes it may be end, and sometimes it may be middle. So for general case, we will consider we are given a position and we want to insert an element to the linked list. Similarly, delete means removing an element from the linked list and then deleting the node. In this case also we'll assume we are given a position and then we want to delete that node from the linked list. Third is search. Searching involves searching through the linked list one by one from the starting and then returning the position of the node if the value is found inside the node. And finally size, which is sometimes even the optional, which returns the total number of elements or total number of nodes that are present in a linked list. So inserting a new node, this is how we actually insert a new node. We'll see in detail when we go through the operations, but basically we just make an existing node point to the new node and the new node point to the next node. So this way we don't have to move elements, and then our linked list our linked list is updated with the new node. Similarly, when we have to delete it, we just delete by making the previous node's pointer point to the next node, and the node in between gets deleted. So this is a general idea of insert and delete. So let's now see how linked lists is normally implemented. Now for simplicity we will consider that we have a singly linked list, which means we only have a single link from each node, and then the linked list is not circular, it's a simple single linked list. But then if you want to see the complex linked list, which is the AA linked list or the circular linked list, they will follow similarly, which is just a little more complicated. So normally to implement a linked list, as we already have discussed slightly, there is a node, and then the node has 2 parts. One is the data and the next pointer. So whenever we want to implement it in any language or or as part of an algorithm also, so we have to first define a node structure. So node structure which has data, and then there is a next pointer that points to the next node. So something like this. Now this is a node wherein the data is 4, and then the next pointer is just a pointer which is pointing to some other node. And as you can see, we will also, because we need to identify the linked list somehow, we have to identify the start of the linked list. We will use a pointer called as a head pointer that actually points to the start node of the linked list. So in this case, head pointer points to the node 4, which is node 4 is the starting of the linked list. Similarly, we can also have a tail pointer, which is optional. Now tail will point to the last node of the linked list. Now in this case, tail points to the 6 because 6 is the last node, and the last node, as you can see, it points to the null, which means it is pointing to basically nothing. And we can also have a size variable or a size member in the linked list, which indicates the current size of the linked list. Sometimes it becomes useful. So similarly, the tail pointer is also sometimes useful, because if you want to insert an element at the end, it becomes very easy if we have a tail pointer. Okay, cool. So that was a general idea of the linked list implementation. And what we normally do is whenever we want to insert or delete an element, we have to make sure the head and the tail pointer has to be adjusted based on where we are inserting the new element, whether at the start, in the middle, or the end. Because if we have to insert the element at the start, we have to make sure that head points to the new element, and similar case for the tail. Okay, cool. Now let's start with each of these operations of the linked list. We'll start with first the insert operation. Now here we are assuming in general we want to insert an element at a particular position in the linked list. Of course, there will be special cases when we want to insert the element at the end or at the start, but we will consider the general situation. So what is the first step? The first step is to first take the new element and then create a node, which means put the value of the new element into a new node and then make sure its next pointer exists. Then the next step is we check if the list is already empty. If the list is empty, what we need to do is the head pointer would be pointing to null. So we have to make sure the head pointer is now pointing to the new node, and then we are done because there are no elements and now there is one element. Otherwise, what we do now, if we want, otherwise we are given a position and we want to insert our new element to that position. So what we do is we traverse or we go to the node at one location previous to the position. So which means if the position is 5, we will go to the 4th node. Now once we go there, we will make the previous node's next pointer point to the new node, and the new node's next pointer point to the node at the position. So let's see this with a small example. Now this is the same example which we had. Now let's say we want to insert an element 37, and then let's say we want to insert it before 99, so that's the position, but then we want to insert it after 12, which means before 99. So what we do is we go to the node which is previous to 99. Now the previous node is the node 12. Once we reach there, what we do is we make the previous node's pointer point to the new node. So which means the nodes or the previous next node is pointing to the new node 37, and then we make the new node's next pointer point to the node at position. So 37's next pointer now points to the position, which means the node which is 99, and then we are done. It's as simple as that in a linked list. And then we don't care about the head pointer or the tail pointer because the head pointer will be somewhere before here. So this is how it is. And similarly, there is a special case when we want to insert the element at position 1, because head will be pointing to the position 1, and then we have to make sure we insert the new element and then we make head point to the new element. So we'll see that shortly when we go through the algorithm. So that is what we will do next. So here is the insert algorithm. So the insert algorithm or the procedure, as we see that it takes 3 items. First is the list, which might be empty or an existing list, and then it takes a position where we want to insert the element, and then the item that needs to be inserted to the list. So the first step is we take the item and then we first form a node, which means we put the value inside the node and then we create a pointer which will point to a location later. So the first step is to just create a node. The second step is the special case, which means if we see that we need to insert the node at the first position, which means at the head position, then we need to specifically adjust the head pointer. So in this case, what we just do is we make the new node's next point to the head, which means point to the first node, and then we make the head pointer point to the new node which we have created, and then we are done, because head now points to the new node and the new node points to the first node which was earlier, and that's what we need to do. But in all other cases, what we need to do is we need to go to the previous node of the position. So that's why what we do is we start with the previous pointer that first starts with the head, which means the first node, and then for I equals to 1 to position -1, so which means we, for n position -1 times, we make the previous node move that many times in the linked list. So, and during this we also check if previous is null, which means if the position that we are entered is out of range, which means the position itself doesn't exist in the linked list, so which means there is a problem. So in that case what we do is we just print an invalid position and then return. Otherwise we move the previous pointer, move that many times till we reach the previous node of the position. And once we have done that, then what we do is we do our movement of pointers, which means the new nodes next now points to the previous next, which means the node which was earlier at position, and then we make the previous next point to the new node. Now let's see this with an example so that things will be more clear. So first, let's say we have 3 nodes in our linked list, where his head is pointing to the node 4, and then we have the last node 6 which points to the null. And let's say we want to insert an element 9 at position 1. Now this is a special case, as we have already discussed, which means we need to insert it at the first position. So in this case what we do is in step 1 we create a new node, and that is what happened here. A new node is created. It's step 2 we check if position is 1, which is true because in our case we want to insert at 1. So this is a special case, and we just go to step 3, wherein we make the nodes next point to head. So how does it look like? So let's say 9's next, which means the pointer will now point to 4, which was our previous head, and then head will now point to the node which is our new node, and then we are done. So this is a special case for inserting node 9 at the first position. Alright, cool. So let's see the different insertion wherein we insert the node to a different position. So let's say we have the same linked list 4 3 6, where head is pointing to the first node, which is 4, and then we want to insert 9 at position 3 this time. So position 3 means, let me number those nodes. 4 is at 1, 3 is at 2, and 6 is at 3. So which means we want to insert somewhere here, because we want 9 to be the third node. So what should we do? Now in this case what will happen is we first create the node which is similar to before. In the second step we have position equal to 1, which is not true, and hence we will jump step 3 and we'll go to step 4. Now in this step 4 we'll have a previous pointer which starts from head, and then we will move our pointer. So let's say previous pointer here points to 4, and then we'll have to move position -1, which means 2. Position is 3, position -1 is 2, so we will have to move from I to 1 to 2. So first time I is 1, and in this case we go to step 6 and check previous is not null because it's a valid node, and then we go and do previous equals to previous dot next. So previous will now move to the next, and then we will increment I, so I will become 2 and 2 and 2. So which means we have already reached 2, so this the for loop will not be executed anymore, and we will then go to step 9. So which means essentially, because the value was 2, we moved the previous pointer once, which means previous pointer now points to 3, and then we will execute the final step, which is node dot next is previous dot next. Now in this case node dot next is 9's next will point to previous next, which is 6. So 9 will point to 6, and then we'll make the previous dot next point to node, which means we will point 3's next to 9, and then this is our insertion. So our insertion is done. So what this will result in is we'll have 4 nodes now, and 9 will be inserted at position 3. So what we did is we just moved around pointers, and then we basically incremented our linked list. So it was as simple as that. Now compare it with an array, where if we had to insert an element at a position, we would have to push all the elements to make space for it, because array is contiguous. So this is a great advantage compared to an array. Cool. So now let's go ahead and see the remove operation. Remove operation is tactically pretty similar, so which means we do a similar process. So to remove an element from a position in a linked list, what we do is, if we see the first node is to be removed, so if we have to remove the first node, then it's a special case. So we'll have to make head point to the second node, and then delete the first node, and then return. Otherwise, we move to the node one location previous to the position, and then make the previous node's next pointer point to the current node's next pointer, thereby deleting the current node. So something like this. Let's say we have to delete the node 99 here, and 12 was originally pointing to 99, and 99 was pointing to 37. So this is what it was originally. So to delete the node 99, we have to do very simple step. We have to first reach the 12, which means the previous node, and then we just make the previous node's next point to the current's next, which means we just make the pointer here point to 37. Thereby we delete this node, and we can remove it, and our deletion process is done. So now let's see it in the algorithm. So let's say we have removed, we are given a position to position which node we will delete, and then we are given a list which contains certain nodes or an item. So first step is again special case. If position is 1, so what we just do is simple thing, we just make head point to head dot next, and then return. So which means we just move the head pointer to the second node, and then return. Now remember, in some languages you might have to even free the node, delete the node, so that its memory gets allocated, but for simplicity we are just not explaining it here. Like if you use C language, you might have to free the memory, so that it doesn't cause a memory leak. But for simplicity, let's not go into that detail. Now otherwise what we do is, if position is not head, similarly we start with the previous pointer which starts at head, and we will move the previous pointer to position -1 times, thereby checking that the previous dot next, which means the node which we want to delete, is actually not null. So which means the position that we have is actually a valid position. So that's why we check in step 6, if previous dot next is null, then actually there is nothing to delete, because the position itself doesn't exist. So we'll just return in that case. Otherwise we just keep moving, which means we move the previous to previous dot next till we reach position -1. Once we have reached position -1, we have to delete the current pointer. Current is previous dot next. So what we make sure, we make the previous dot next pointer point to previous dot next, which means the next to the current pointer, and then we are done. Now let's see this with an example. Now similarly, let's take the first special case where we want to delete the first node, which means we delete actually list 1. Now in this case we have to delete node 4. So in this case what will happen is, we will go to step 1, we'll check position is 1, and then we will execute step 2, and then we will return. There is nothing much to be done. So what we do is, we just make the head, we delete the node, and then we just make the head point to head dot next, which is the next, and then we are done. We don't have to do anything. The linked list earlier had 3 items, now it has 2 items. It's as simple as that. Let's see the other case, wherein we have 3 nodes, let's say 4, 3, 6, and we want to remove the second position, which means node 3 here, because 4 is node 1, 3 is node 2, and 6 is node 3. Now in this case we will not go to the if condition, we'll come to step 5 actually, and then we will use a previous pointer here. So we start with so this is our node. We start with previous that points to the head first in step 4, and then position minus 1 times, which is 2 minus 1, which is 1. So which means we will actually not go into this loop because I is already 1, so we just skip the for loop here. We don't have to move it here because position is 2 and position minus 1 is 1. So we will just go to step 9 directly. In that case, what we will do is we will just make previous dot next, so which means 4's next pointer will now point to previous dot next, not next, which is the 6. So thereby skipping the node here, which deleting the node here, will just make the next pointer point to 6, and then we are done. So this way 3 is deleted and then we only have 2 nodes in our list. So it's as simple as that. Awesome, cool. Now let's see the next operation, which is search operation. So search for an element in the linked list. So which means we are given a number or a value and we want to go through the linked list and see if that element exists, and we will return its position. So what we do is we just use a counter. Let's say a position counter will start at 0, and then we'll traverse each node one by one from the head pointer, now similar to the previous pointer which we had, and then we increment the position and compare its data with the element. So we keep going one by one and we'll check if we have found the element. If we have found the element, we just remove the return the position value. If not, we will just return -1 saying the element is not found. So it should be something like this. Let's say we have 4 nodes in our list here and we want to search for an element. Let's say we want to search for an element 6. So we start with position is 0 first, and then we will have we will traverse through each node. We'll first traverse through 4, and that way we'll update the position counter to 1. We'll compare 4 with 6. We'll see that 4 doesn't match with 6. Next we will again increment position to 2. We'll compare 3. There is no match. Then next we will move a position is 3, and we will see that there is a match, 6 equals 6, and then hence we are done. So we will now return the value 3, and that's what it is. So 3 is the output of the search. Now let's see this as an algorithm. So let's say we want to search through a list and we are searching for an element or a key in the given linked list. So what we do is we start with position is 0, a variable, and then we'll start with a pointer current which starts with head, and while current is not null, which means while we keep on moving through the list and then incrementing our position, and in step 5 we will compare the data. If we have found the data, then we are done. We just return the position, else we keep moving, which means else we move the current to the next pointer. And finally, if we reach a point where current is null, which means the list is over, we have not found the element, and hence we go and return -1. So this is how it looks like. Let's now apply this algorithm to the list which we had. Now let's say we want to search for the element 9 in this case. So what we do is we start with position is 0 in step 1, and then we'll make current point to head, and we will go to step 3. We'll check current is not null, due to which position will be incremented to 1, and then we'll compare the data with the key, which means 9 with 4. It won't match, and hence we'll increment again. We'll increment the current pointer. So this way current now moves to the second node, and still current is not null, so position will be incremented to 2. Similarly, we have next step, current will point to 6 and then position is 3. Next we will have current point to 9 and position will be 4. Now at this point what will happen is step 5 will be true. Why? Because current dot data, which is 9, is equals to 9, and hence we will return the position, which is 4. So we are done here. So finally the search method will return 4 as a result of the search call. Okay, cool. Now let's see the optional operation that we have, that is to find the size of a linked list. Now to know the size of a linked list, actually the idea is pretty similar to search. We just traverse from the first, use a pointer, use a variable and keep incrementing till we reach the null pointer or the final. So what we do is we initialize a counter to 0, traverse each node one by one till the last node, and then increment the counter, and finally value of the counter is the size of the linked list. So something like this, let's say we have 4 nodes here, we start with size equal to 0 first, and then we will increment a variable or a pointer, kind of a current pointer that points to the first node, then size will be 1. As we move the current pointer, we keep incrementing the size, and finally when current reaches the last node, after which current will become actually null, and then the for loop will stop. So size equal to 4 will be returned, which is the size of the list. Now let's see the algorithm real quick. So size, it only takes the list and it returns the number of nodes in the linked list. So we start with a variable size, initialize it to 0. We'll start with a current variable or a current pointer that points to head, and while current is not null, we keep incrementing the size, and then we keep incrementing the current. Whenever we reach the null pointer, which means we have completed the traverse through the entire list, at that point we just return size. Now again, applying this to an example, let's say we have 4 nodes in our list and we have a head pointer that points to the first node. Then we start with size equal to 0, current pointing to head, and then size is 1. Then current points to the second node, size is 2, current points to 6, size is 3, current points to 4, size is 4. Then current will point to null, and once current points to null, our while loop will break and we actually return the value of size as 4. Alright, cool. So that were all the 4 operations that we saw: insert, remove, search and size. Now let's go ahead and see the time complexity of each of these operations. In fact, if you have noticed, the insert or remove operation is pretty similar. What it does is there is only one for loop which runs through position -1 times, because we need to make the previous pointer point to the new node, or to the, in case of insertion, or point to the next node in case of deletion. So essentially this is the only loop which we have, and it runs position -1 times, and hence the total operations is position -1. And in fact, because position can be the end of the node, end of the linked list, which means it can be, we need position might be n. So there it's possible that the for loop runs n times, and hence we say this as an order of n. So total operations for insert and remove is actually order n, because in worst case insertion deletion is at the end. Now similarly for the search and size operations, which were pretty similar, we had a while loop, and the while loop actually ran n times, which means to the total length of the list, whatever it was. And hence in this case the total operations, now in case of search actually it stops if we have found the node. If we have not found, then it is n times. We'll assume that we are in the worst case, and hence it is n times. So total operations for search is k if the element was found, otherwise it's order n in the worst case. Similarly, total operations for size is actually order n, because we need to traverse through the entire list to get the size anyway. So hence all these operations, insert, remove, search, size, all are actually order n. Now which you might think that it is a little higher than in array, wherein if we want to, in some cases, because in some cases it might be easier to insert an element. Let's say we want to insert an element at the end of the array, then we can directly access the end of the array and then insert it. There is actually, it's not order n, but in case of linked list we have to traverse through from the start to the end. So here is a summary of all the 4 methods. All the 4 methods are actually order n. You can see in certain cases, let's say if we have a special case wherein we want to insert at head, we can do it in order 1. Similarly, if we have a tail pointer, insert at end could be also in order 1, which means we don't have to traverse the list. Similar thing happens with delete also. If we want to delete, this shouldn't be insert, this should be delete at head and delete at end. Can be, you know, order 1 depending on the implementation if we have an additional tail pointer. Now search would be, in the worst case, we need to traverse the entire list, and hence it's order n. And size has to be always order n because we need to traverse through the entire list to, you know, get the size. Alright, cool. Now let's see different variants of linked lists that are possible. Now these will be a little more complicated to implement compared to the singly linked list which we saw in this video, but it could be achieved very easily by, you know, additional variables or additional member variables. So the first is doubly linked list. Now doubly linked list is basically a linked list wherein every node has 2 pointers. Similar to a next pointer, there is also a previous pointer which points to the previous node. So this makes certain operations easier. So you can traverse both directions, left or right, you know, previous, and then next. There is also a circular linked list where the next node of the last pointer points to the first node. So in this case, what happens is, if we have traversed the list once and we reach the end, we can easily reach the first node by just making one next operations. So useful in certain cases. Then there is a multiply linked list, which becomes a little more complicated, where nodes not necessarily contain 2 links, but it may contain multiple links pointing to, you know, other nodes. So this can be useful in, let's say, building a tree or some other complex data structures. So here is a doubly circular linked list where you can see every node has 2 pointers, and the next pointer, and then there is a previous pointer. So the next point, let's say for 99, the previous pointer points to 12 and the next pointer points to 37. And also it's a circular linked list, which means the last node's next, which is 37's next, points to the first node. Okay, cool. Looks like we have now reached the end of the video. I hope the explanation of the video made some sense. It gave a little more, you know, understanding of how linked list is in detail. Now before we end, here is an exercise for you guys to try it out. It's pretty simple exercise and you can really easily do it if you have followed the video, you know, properly. So now in this, for the exercise also, we are assuming we have a singly linked list. Now we have an empty linked list first, and let's insert 4 elements: 5, 10, 12, 8. I would recommend you to, you know, draw the structure, how it looks like on pen and paper, so that it makes understanding much more clearer. Then let's insert 7 at third position in the linked list. Now the linked list already has 4 items and we need to insert 7 and see how it looks like. Then we'll call the search method to search for element 10 in the linked list. Next, go ahead and delete node 10 and 8 from the linked list. Next, delete the element at the second position in the linked list. Next, find the size of the linked list. And finally search for element 10 again in the linked list to see in which position it is. Alright, you know, you can do all these on pen and paper, so that understanding of the insert and insert, delete and various operations is, you know, is pretty clear to you. And if you are really confident, you can even go ahead and, you know, use a language like Java or C or C++ and implement the linked list, and, you know, print out the output of the linked list to see how it goes. Cool, so we have reached the end of the video. Thanks guys for watching. If you really liked it, I would you know, request you to, you know, spread the news and you know, share and subscribe to our other videos. So bye bye for now. See you again in the next video.